This is section 11.3b. I just feel like there's some problems that would benefit you to work through with me. So number 22 says the sum from n equals 2 to infinity, natural log of n over n squared. So before we use it, we need to stop and think, are the conditions met? Is it decreasing, continuous, and positive? So let's look at that graph. As you look at the graph, you can see that it's definitely increasing starting at 2. Remember that we're dealing with sequences. So it's 0 at 1, and then it goes up, and then it goes back down. But our next positive n value is 2, so that's why we started with 2 on this. I'm going to kind of leave the graph in the corner. So that means it is positive, it is decreasing, it is continuous. So let's look at the integral from 2 to infinity. Natural log of n over n squared. These are x's. Natural log of x over x squared dx. Yeah, when you have those problems, I understand. I do too. The limit as, it's an improper integral, so the limit as m approaches infinity from 2 to m. Let's call this x to the minus 2 ln of x dx. Now, u sub is my favorite choice, but if I let u equal natural log of x, du is 1 over x dx. And notice that over here there's an x squared. So there's too many x's to do u sub. So my next thought is integration by parts. So let's look at this one. So we take natural log of x always goes here because we know the derivative to be 1 over x dx. So that means in my dv I have x to the minus 2 dx. So if I integrate x to the minus 2, I get x to the minus 1, and there's a negative there. So that's the same as negative 1 over x. So now we can say the limit as m approaches infinity. Now I have uv, so I'm going to put my v first. Negative, the limit goes to the whole thing. Negative 1 over x, natural log of x, and this is already evaluated from 2 to m. It's already integrated. Minus the integration of negative 1 over x times 1 over x dx. From 2 to m. Now, 2 negatives here make a positive, so we can change these to be positive. So we can say the limit as m approaches infinity of negative 1 over x, natural log of x, from 2 to m, plus the integration from 2 to m of x to the minus 2 dx. Well, that's a nice, easy integral, isn't it? It should be. It's in the middle of integration by parts. So we have the limit as m approaches infinity, negative 1 over x, natural log of x, plus, actually this turns to a minus, x to the minus 1 from 2 to m. Now I could move my bounds to the end because everything is in those bounds. And I'm tempted to factor it out, but I'm not going to because it's easier to see if you don't. So I'm going to call this negative natural log of x over x minus 1 over x from 2 to m. So let's look at the, plug in the bounds. So we have negative natural log of m over m minus 1 over m. Okay, and then we have minus, so let's put a bracket here, parentheses, negative natural log of 2 over 2 minus 1 over 2. Close bracket, because the limit applies to all of that. Now, this second term down here is constants, but we can distribute that negative. See the negative getting distributed? Life is pretty there. And here I have 1 over m in this term right here, and 1 over infinity goes to 0. Now, the problem is this mess right here, because if you look at this first term, I have infinity over infinity, or negative infinity over infinity, however you want to look at that. But either way, it's an indeterminate form, so you have to use L'Hopital's rule from here to here. So let's look at L'Hopital's rule. So we say the limit as m approaches infinity, and that says the derivative. So we have negative 1 over m, because that's the derivative of natural log of m, over 1. Now the next term is gone, so I'm going to say plus 1/2 natural log of 2, plus 1/2. So my limit's only applying here. Now, we can go back to here where 1 over infinity is 0. You might have cheated mathematically and gotten that, but you should be using L'Hopital's rule. 1/2 natural log of 2 plus 1/2 is our answer. Now it's prettier to say natural log of the square root of 2 plus 1/2, because remember that 1/2 could be a power. Either way, this is convergent. And since it's convergent, then we can say, therefore, the problem said that the sum from n equals 2 to infinity of natural log of n over n is convergent. So all the techniques of integration you used before are still possible at this point. Take a minute and look at this next problem, number 24. If you were in class, I would say pause this video. Well, you're not. Anyway, I say pause this video and practice it, and then come back after you write the problem down. So we have the series of k e to the minus k squared from 1 to infinity. Pause the video. In 2 seconds, I'll give you a hint. So if you came back from the hint, we can use the integral test, and we're going to want to use u sub. So we're going to rewrite it to look like this. Note that k is your variable. Very bad choice of variables in my opinion, but these should be x's instead of k's anyway. But use u sub and then come back. Go ahead and try it. Some of you don't want to. So we have the limit as m approaches infinity, 1 to m, x e to the negative x squared dx. So let's let u equal negative x squared, and du is negative 2x dx. So dx is negative 1/2, 1 over 2x du. So we have the limit as m approaches infinity from the integral from 1 to m, and I have x e to the u, and then our dx becomes negative 1 over 2x du. These x's cancel. So we have the limit as m approaches infinity, the integral from 1 to m, we have negative 1/2 e to the u du. You can't integrate e to the minus power. You can only integrate e to the u. No variations of that. Just e to the u. So we say the limit as m approaches infinity, and that integral is negative 1/2 e to the u from 1 to m. Now we need to plug u back in. So we have negative 1/2 e to the negative x squared from 1 to m. Now I'm going to deal with that negative exponent right now. I'm going to say negative 1 over 2 e to the x squared from 1 to m. It's a little easier to see your limit in that case. So we have the limit as m approaches infinity of negative 1 over 2 e to the m squared. That's a little hard to read. Let me see if I can make it a little bigger. Minus negative 1 over 2 e to the first squared, which is e to the first. Two negatives make a plus, and then let's think about this infinity. E to the infinity squared is infinity, and e to the infinity is infinity, and so this goes to 0 because we have infinity in the denominator. So this equals 1 over 2 e to the first, which is e. So this improper integral is convergent. That means that, therefore, the sum from n equals 1 to infinity of k e to the minus k squared, so this is a k, is convergent. So we've done an integration by parts. We've done a u sub. Let's do one more, maybe two. Number 26 is one that you need to have seen. We haven't done one like it yet. So we have the sum from n equals 1 to infinity, and we have n over n to the fourth plus 1. When we look at the graph, it is decreasing, positive. I don't need to look at the graph. Your n values are positive, so everything there is positive. So we definitely have positive. Decreasing because the number on top is smaller than the number on the bottom. Continuous, by definition, I'm good with that. So we can look at the improper integral. So let's look at the integral from 1 to infinity of n over n to the fourth plus 1. Again, these should be x's. Let's try that again. X over x to the fourth plus 1 dx. The limit as m approaches infinity from 1 to m. And then we have x over x to the fourth plus 1 dx. Now here's the problem. X to the fourth, you can't use partial fractions because it's not factorable. We don't have anything about partial fractions past the quadratic stage, past x squared. It's not triangles. It's not trig identities, but that does look like inverse tangent. So let me think about it this way and say the limit as m approaches infinity from 1 to m, x over x squared plus 1. Do you see inverse tangent on the bottom? The problem is for inverse tangent, you need a 1 on the top. So I'm going to erase this and go back. That's where I'm headed with it. So I can use u sub, and let's let u equal x squared. Then du is 2x dx. So dx is 1 over 2x du. So now we have the limit as m approaches infinity. The integration from 1 to m of x over u squared plus 1 times du, which is 1 over 2x du. So these x values cancel. So we have the limit as m approaches infinity from 1 to m. And now we have 1/2 times 1 over u squared plus 1 du. Do you see inverse tangent happening now? A equals 1. So we have the limit as m approaches infinity, 1/2 parentheses 1 over 1 times inverse tangent of u over 1 from 1 to m. So we have the limit as m approaches infinity. I feel like we did an inverse tangent earlier. 1/2 inverse tangent of u, and u is u squared. It's not u. U is x squared from 1 to m. So we have the limit as m approaches infinity. We have 1/2 inverse tangent of m squared minus inverse tangent of 1. Now think about your tangent. Inverse tangent says what angle gives me this tangent value. So here we have negative pi over 2 to pi over 2. And tangent looks like this. So as I approach infinity, I get pi over 2. So this means we have 1/2 pi over 2 minus, sorry, don't close that parentheses. 1/2 pi over 2 minus the inverse tangent of 1 is pi over 4. So we have 1/2 times 2 pi over 4 minus pi over 4. So we have 1/2 times pi over 4, which gives us pi over 8, which is convergent. Now we go all the way to the answer. Don't stop. So since the improper integral is convergent, therefore the sum from n equals 1 to infinity of n over n to the fourth plus 1 is convergent. There's a couple problems in there where they're partial fractions and u sub, and just be careful as you do your homework. Number 25, there's one in there, one or two that could be partial fractions. So if you have any problems or need any help, let me know. Thank you.